Okay, so we're now recording. So we're going to talk about Unit 2, or forces in uniform circular motion. So we did forces during week 2. Make sure you know the terms. Make sure you know velocity, force, acceleration, equilibrium, inertia, weight, normal force, true weight, gravitational force, applied force, tension, blah, blah, blah. Actually, some of you probably don't need to know. Probably should have crossed these off. Yeah, we never really talked about this. We never talked about satellites or orbits. The baseball, the pitcher one on the lab simulations was on orbit, and I just realized we shouldn't do that. We didn't do any of these here, but the other ones I think are fair. So fundamental forces. I mean, a lot of that's just going to be like knowing force due to gravity. Force due to friction. Normal force. Applied force. Net force. So make sure you come for all that. Your notes should help you there. If you kind of look at your notes. Yeah, so like a lot of stuff on forces, fundamental forces right there. We kind of talked about a lot of that stuff and like the diagrams, so yeah. So definitely I think that would be good, or weight and gravity, all that fun stuff. Difference between little g and capital G. So capital G is a constant. That's actually over here. It's something that you use for this formula. That's when you're trying to find the gravitational attraction between two bodies, like maybe myself and the Earth. The Earth obviously is more massive than me, and there's a certain distance that I have from the center of the Earth. So that would kind of explain the gravitational force that my body experiences, and it should come out to actually 9.8 if I do it, or close enough if we do it correctly. If you solve for the acceleration, you should get about 9.8 if I use my mass here. So G, this right here, that should actually be, so the mass of the Earth divided by r squared times the constant should be about 9.8. So if I were to plug this in, and then capital M and R, so actually if I do that right now, if I get 6.673 E negative 11, come on, man, 6.673 E negative 11 times the mass of the Earth, which is 5.98 E 24. Yeah, it's kind of hard to see, but if you see there, like that's kind of what I did. But then I got to divide that by the radius of the Earth, so 6.38. I'm going to do a double parentheses so I can protect it. 6.38 E 6 squared. Yeah, you see I get like 9.8. So that's the difference between the two. G is a constant, little g, capital G is a constant, little g is actually acceleration on Earth. Static kinetic frictional forces. We're going to connect frictional force is like the frictional force you experience when you're in motion. Static is when you're not moving. So like right now, see my planner and pencil are not moving, right? But if I move it, then all of a sudden I'm doing kinetic friction. I know your 3 laws of motions. We talked about that. I might just put some conceptual questions on the final. Newton's laws right here. First law, second law, third law. So make sure you know all that. Hold on a sec. Difference between mass and weight. So remember, weight is actually a force. It's your mass times your gravity, where mass is just how much matter you take up, and that's just done in grams or kilograms. And I guess we do pounds in this country, but it's a conversion, but that's what's happening there. What forces do you draw in a free body diagram? So going back to this stuff here, so probably a good idea to, you may even want to watch some of the old videos. If you kind of go to the dates, you can kind of watch that stuff, but just make sure you kind of know, like, okay, Normal force is always perpendicular to the surface. This is static friction, which is obviously parallel to the surface. Weight's always going down the middle, and you can break it down to its components. And remember, force due to friction is going to be the coefficient kinetic friction, or the coefficient static friction times the normal force. And to figure out the normal force, it's always going to be, because you're not moving this truck off the surface, just going up and left or right. It's not lifting, it's not levitating. So normal force will actually be the same as the weight in the vertical direction. So the W or the W perpendicular, I guess, the weight that's perpendicular to the surface. Whereas the weight that's parallel to the surface will counteract the kinetic force, as we've talked about before. So make sure you're comfortable with all that stuff. Centrifugal force is a little different. We didn't talk much about that, but centrifugal force is a formula for that. It's just mass times just centrifugal acceleration. We did talk about centrifugal acceleration, which is r omega squared, or v squared over r, same thing. And obviously, when you're dealing with centrifugal force, your acceleration is always going to be pointing towards the center, and your velocity is going to be pointing tangentially. So you're always going to be having acceleration because your velocity is always changing. So even though the speed might stay the same, the direction is always changing when you're in circular motion. So you're always going to have some sort of centrifugal acceleration. I don't know if I'll ask too much about that because we haven't really done too much on that stuff. But those are all a lot of just conceptual stuff. And if you look at the answer key, they don't start the answer key until about number 7 or so. So 9 is really when they kind of start doing some work. So let me kind of briefly talk about, we skipped 13 because we didn't really do elevator problems. But 9 through 21, except 13, so that's a total of 12 problems you guys do when you get back from the break. But kind of just briefly talk about these here. 100 Newton force, acts as 75 kilogram person. Remember, F equals ma. That's really, really easy. I mean, that's kind of like just a throwaway question. And my stylus died. Don't know why it died. I haven't been using that much this morning. Yeah, so F equals ma. That's easy. For 70 kilogram ice skater pushes on a box on a smooth ice, no friction, applies 200 newtons against the 50 kilogram box. What acceleration is the ice skater and the box? So remember, if you're pushing horizontally, that's your applied force. And yeah, the system itself, because it's 120 kilograms, so that's kind of what you're gonna do there. You do have the normal force and the way the box kind of cancel each other out. Yeah, hold on, let me make sure I'm reading this carefully. What's going on for 10 again? Okay. So you do have the weight of the skater. And you do have the weight of the box itself. And I suppose that the skater's kind of, does it move? Hold on a sec, let me look at this one more time. Yeah, it does move, obviously. So you do have, the force that's being pushed on against the box because the force is going in the right direction. So you have that acceleration. And then here, remember the box is pushing against the skater as well because you have that, equal and opposite reaction. So you have the acceleration of the skater in that direction as well. I'm not sure they calculate the weights though. I don't know how that helped us. That seemed kind of confusing. Yeah, just F equals ma and just do that. And then of course 11, yeah, so you will need to actually calculate the weight and then break it down to its parallel and perpendicular components. And then you'll need to get the normal force. Actually, no, it's frictional, so you don't need to worry about that. So yeah, so in this case, then you really just are finding the the parallel weight, I guess. Yeah, so in this case, you're doing this. And I don't want to take too much time, but for 11, so you have a block, and you have your weight. Your weight is 10 times 9.8, or let's do it over here. You have your perpendicular weight and your parallel weight. We're really interested in the parallel weight because that's what's bringing it down. The 6 degrees actually goes right there. And that's kind of weird. I mean, it's also right here as well, but those are going to be equivalent. So to get the parallel weight, you take your weight times the sine of 60 degrees. Your weight, again, is going to be 10 times 9.0, or 98 newtons. Sine 60, I think, is root 3 over 2. If you know your trig, or you could use a calculator, it's 0.87, 0.6 something. Yeah, so if you do that, 98 times root 3 divided by 2. So it's about 84.87. But remember, you're going to set this equal to your net force. And because there's no friction, you don't have to worry about that. Net force is only going to be the parallel weight, bringing it down. That's MA. And remember, your mass is 10. So the exertion is going to be a little less than associated to gravity because it is on a ramp. We kind of expect that to happen. So you should have an exertion of about 8.49. That could be a good final exam problem. 8.49 meters per second squared. So that's how you can kind of look at 11. And yeah, they kind of do a lot of, yeah, kind of the same stuff I was doing anyway. And it should be negative because it is going down. But yeah, I won't trick you with the signs so much, but just make sure you get the magnitude. 12. A stoplight suspended by 2 cables over a street. The weight of the light is 110 units. The cables make a 760-degree angle with each other. Find a tension in each cable. So you're going to actually do a free by diagram here as well. So here are your cables, and here is the sign or light, and it's weighing it down 110 newtons. So these are your tensions. And we could probably split this down the middle. If it's 116, these are each 58 degrees, you know? And you're going to tension in the y direction. So if you kind of like do that. And what else do we know? Yeah, that's 58 degrees. That's t, so that's ty. So the cosine of 58 degrees is going to equal ty over t. And I'm really interested in ty because you're going to have 2 tensions. So overall, this is not moving. So our net force is 0. Overall, this thing is not moving. And your net force is actually going to be both tensions of the cable minus the weight due to the sine. And so ty is going to be t times, cosine 58. Easy peasy. So you're just doing that, t times, and that's going to be 0. So really hard to do this with my mouse. And your weight's 110. So you kind of just move things around. 110. This one I like a lot too. And then divide by cosine 58. So tension each cable is about 103.8. newtons. That's what I wind up getting when I work it out. And we kind of look at their solution key. Yeah, they get the same thing. And it's set up the same way. So you could do that also, I suppose, but that doesn't really help us so much. I mean, you kind of know that they're going to be the same. But yeah, I think the way I did it was better, to be honest with you. 13 we won't worry about. We didn't really do those problems. 15, remember normal force. So your normal force, we're assuming this is on a flat surface, so 5,000 kilograms times 9.8, that's the weight due to gravity. Normal force is going to be the same thing, times 0.5. There you go, easy. 16, I think, is fair. Make sure you not convert degrees to radians. We have that conversion right here. Just so you know, 2 pi radians is 306 degrees, or pi radians is 180 degrees. For those who haven't done pre-calculus yet, you're welcome, because this will be something you have to do in the fall or spring whenever you do trig. Yeah, you have centrifugal acceleration, the radius, the speed. That's easy. We have that formula right here. V squared over r. I think that's fair. 18 was find the gravitational force of attraction between a girl and a boy is in 0.5 meters apart. So boom, there you go, and you got capital G right there. You guys should be fine for that. 19 was acceleration due to gravity and altitude of this above the surface. So you have the radius and you have the okay. You have your distance above the Earth, but then you also have the radius of the Earth. So actually, the total distance that you are from the center of the Earth is this plus this. So it's 7.36 times 10 to the 6. And you use the mass of the Earth, which is right here, and plug into this formula, the little g formula, because you're going to solve it for because once you're in outer space, you're a little more weightless, right? Which would make sense because you're further away from the center. That's kind of why you feel weightless when you go to, well, none of us have been in outer space. So if you do, that's why you feel weightless the more you're leaving the center. Of course, as you might get to another planet, there's a gravitational attraction there, or the moon, but the moon has a light one too. Here you have 4 people pulling on a rope, and they're pulling on in different, two to the left, 2 to the right. Magnitude is 5 kilograms. What is magnitude? Sorry, of the 5 kilogram, 5 kilogram rope. So you should be able to get the net force. You'll be able to get the acceleration there. 10-gram nut is hanging from a spring that has stretched 30 centimeters. So if F equals kx, we know this. So we'll need to get the spring constant, because then the scroll's pulling on it. It causes that kind of stretch. But yeah, 10 grams hanging from a spring that's stretched because the scroll's pulling it down. Got it. Okay. So those are all good ones. What we'll do, I think those are all fair problems. So I've done some of these already, but I'll have you do them anyway. So let's take a lunch break. Let's come back around 12-ish. So I'll be back on by 12:05. But by 12:10, let's get started. I'll probably give you guys about 30 minutes to do these problems. And then around 12:40-ish or so, we'll do Unit 3, and I'll probably need about 15 minutes to talk about that. And then it'll be about 1 o'clock, and then you guys will do some problems there. Then we wrap it up. So this is perfect. This is exactly what I had envisioned. So you guys are getting a lot of good review here. But yeah, let's do lunch break right now, and I'll stop the recording.